On June 3rd, 2026, Japan fired the most serious weather warning its new national system allows. Level 4. Danger warning. Get out now. That warning went to over 1.6 million people across Tokyo, Kanagawa, and Chiba. Reporters went to the shelters to document the response. The shelters were empty. One person had come in. One person, and they went home. Here is what makes that number so alarming. Japan did not just issue a warning. Japan had spent years redesigning its entire national disaster alert system from the ground up. The new system launched on May 29, 2026, just 5 days before Jangmi arrived. The whole point of the redesign was simple. When level 4 fires, you go. You do not wait. You do not think about it. You go. The first time it fired in one of the largest cities on Earth, nobody went. At the same time, in a small town in Wakayama Prefecture, a river called the Koza was already out of its banks. The road out of town had collapsed, and the warning system had already escalated past level 4. It was at level 5. Level 5 means the disaster has already started. The question this video is going to sit with, the one nobody has answered yet, is this. If 1.6 million people ignored the warning when the storm was survivable, what happens the day the storm is not? If you are watching this channel for the first time, this is what we do here. We take events that move through the news in 30 seconds, and we stay with them long enough to find out what actually happened. Mainstream coverage told you Jangmi was a weakening storm. The data told a different story. That is why this channel exists. If that kind of coverage matters to you, subscribe now. We cover earthquakes, typhoons, space events, and volcanic activity. The things your local news moves past too fast. Drop a comment right now. Tell me where you're watching from and what time it is there. I read everyone. And here's the question I want you to hold while you watch this. If you were one of those 1.6 million people in Tokyo that morning, and your phone sent you a level 4 danger warning, would you have left your home? Here is what the data actually says. It begins in Sioux City in the early hours of June 3rd, 2026. A river called the Kumozu runs through this part of the Dakai region on Japan's Pacific coast. Just before sunrise, the river started to rise faster than the gauges along its banks had measured in years. The instruments noticed. The alarm went up the chain, and within minutes, the Kumozu and the neighboring Kumozu-Furukawa River became the first two rivers in the entire Takai region to trigger something called a Level 4 Flood Danger Warning. The warning had only existed on paper for 5 days. It had never been issued anywhere in Japan before that morning. By the time most people in Sioux City had finished their first cup of coffee, the system that was supposed to protect them had already fired for the first time in history. That same morning, about 100 miles to the southwest, in the small coastal town of Kozagawa in Wakayama Prefecture, a different river was doing something worse. The Koza River had already overflowed its banks. Water was moving into houses in the Sukanos district, and at 5:35 in the morning, the Japan Meteorological Agency issued a Level 5 emergency flood warning for that river. Level 5 is the highest warning the new system allows. It means the disaster is already happening. It means the time to evacuate has passed. It means you should stop trying to leave and instead go to the highest floor of the nearest building made of concrete or steel. That was the first Level 5 warning ever issued under Japan's new national alert system. And it came on the system's 5th day of operation. This is the part of the story that most coverage skipped. Japan did not just issue a warning that morning. Japan had spent years rebuilding the entire architecture of how it communicates danger to its own population. The new system uses 5 levels, where the old system used a confusing mix of advisories and special bulletins that residents often did not understand. Level 1 is general awareness. Level 2 is caution. Level 3 is for vulnerable people, the elderly and small children, to begin moving. Level 4 is the new one. It is called danger warning, and it is the level at which everyone in the affected area is supposed to be out the door. Level 5 is reserved for situations where the disaster has already begun. The Japan Meteorological Agency and the Land Ministry switched the country onto this new system on May 27, 2026. The full public-facing launch was finalized on May 29th. By the morning of June 3rd, the system had been live for exactly 5 days. And in that 5 days, it had never been used in a real emergency. There had been no drills, no public test fires, no simulated activations to give residents a sense of what the alerts would sound like on their phones. The first time most of Japan's 124 million residents heard the new alert tone was when it was real. The Japan Meteorological Agency had warned in the weeks leading up to the launch that the new system was designed around a single principle. Move at level 4. Do not wait for level 5. The whole architecture of the new framework was built on the assumption that residents would respond to a level 4 warning the way an old fire alarm in a school building tells you to walk out the door without thinking. Level 5 was supposed to be the marker for failure, the level you only see if something has already gone wrong. On June 3rd, 2026, Level 5 fired before most people had even checked their Level 4 alerts. Here's what a 5-level warning system is in plain English. A 5-level warning system is a way of measuring how much danger is arriving and how fast you need to act. Think of it like this: a pot of water on a stove. Level 1 is the burner just clicked on. The water is cold. There is no immediate concern. Level 2 is water warm to the touch. Pay attention, but do nothing yet. Level 3 is steaming. Older relatives and small children should move away. Level 4 is a full rolling boil. Everyone backs away immediately, no exceptions. Level 5 is when the water has already boiled over and is burning the counter. At that point, moving slowly is the danger. That is what Japan's new warning system is designed to communicate. And on the morning of June 3rd, it went from cold to boiling over in a single morning. The numbers behind the activation are worth understanding in detail. The Level 5 designation for the Koza River covered 2 communities: Kozagawa Town, with 862 households and 1,672 residents in the affected area, and Kushimoto Town, with 755 households and 1,849 residents. That is roughly 2,800 people total. These are not anonymous numbers from a population database. These are the people who lived along that river, the people whose houses started taking on water before dawn, the people for whom the warning arrived after the water did. In Sioux City, the Level 4 activation on the Kumozu and Kumozu-Furukawa rivers covered a different population. Sioux is a city of about 270,000 residents, the capital of Miyazaki Prefecture. The affected zones were the riverside districts where flooding could reach homes within minutes of a levee overtopping. The instruction was the same as the instruction Tokyo would receive a few hours later. Leave now. Move to higher ground or a designated shelter. Do not wait. What most coverage did not mention was that the Kumozu and Kumozu-Furukawa rivers in Sioux City were the first rivers in the entire Tokai region to trigger a Level 4 warning. That activation was happening at the same time as the Koza River was hitting Level 5 in Wakayama. The story was not Tokyo got an alert. The story was that 3 different river systems in 3 different prefectures were hitting the top. 2 levels of a brand new national warning system on its 5th day of operation, all at the same time, before most of the country had even woken up. Inside the Japan Meteorological Agency operations room in Tokyo that morning, the director of forecasting issued a public statement that translated roughly to this: "Please evacuate to safer places than where you are now because your lives are in danger." That phrase was directed specifically at the residents of Kozagawa. It was not a metaphor. It was not bureaucratic language. It was an instruction issued at 5:35 in the morning by a senior government meteorologist to people whose houses were already filling with water. In the same hour, the system was simultaneously communicating Level 4 instructions to over 1 million phones across Tokyo, Kanagawa, and Chiba. Every smartphone in the affected zones received the emergency alert tone. That tone is one of the loudest sounds a Japanese mobile phone is capable of making. It is designed to wake a sleeping adult through a closed bedroom door. On June 3rd, it woke an estimated 1.6 million people in the Kanto region alone. The data tells a different story than the headline. Mainstream outlets across the United States, The United Kingdom and Western Europe covered the morning of June 3rd primarily as a Tokyo weather story. Headlines emphasized the evacuation orders, the canceled flights, the disrupted commute. What the data shows underneath those headlines is something far more specific. Japan's brand new 6-day-old warning architecture was being stress-tested in real time across multiple river systems simultaneously. It was firing at both Level 4 and Level 5 in different prefectures at the same time. This multi-level, multi-site simultaneous activation was the actual news. And it was not reported. 30 seconds on the evening news. Here is the full picture. The Komozu River triggers Level 4 for the first time in Tokai history. The Koza River triggers Level 5 for the first time in Japan's history under the new system. The Tadagawa River in Tokyo's Shinagawa Ward triggers Level 4 for the first time in Tokyo's history. All within the same morning. All on day 5 of a system that had never been used before. There is a research meteorologist named Scott Braun who works at NASA's Goddard Space Flight Center in Maryland. On May 30th, 3 days before landfall, Braun's team was already analyzing satellite imagery of Jangmi captured by the SCI-IRS instrument on the Suomi NPP satellite at 1640 Universal Time. What they were looking at in plain English was a typhoon with an unusually large eye. The eye of a tropical cyclone is the calm circle of low pressure at the center of the storm. Most tropical cyclones at this wind speed have an eye that is small and tight. Jangmi's eye was wide. Braun described it as on the larger end of the spectrum. What that meant was that the storm's rainfall footprint was going to be unusually broad. A small-eye storm dumps its heaviest rain in a narrow band. A wide-eye storm spreads it across more area. What Braun was actually saying, in the careful language scientists use when they speak to the public, was this. Even though Jangmi's wind speed was relatively modest by typhoon standards, the rainfall it was going to produce was going to cover more ground than a typical storm of its category. He did not say that out loud in those words. The data did. By the time the Japan Meteorological Agency was finalizing its forecast on the morning of June 2nd, the storm was about 80 kilometers east-southeast of Miyazaki City in Kyushu, moving northeast at about 40 kilometers per hour, packing winds of up to 126 kilometers per hour at the surface. Those numbers translate to a storm moving at about the speed of a slow highway car, with wind speed equivalent to a Category 1 hurricane on the Saffir-Simpson scale used in the United States. In American terms, a serious storm but not catastrophic. That Category 1 classification is part of why so many residents stayed home. The wind numbers did not look terrifying. The radar images did not show the kind of compact, intense eye that signals a major hurricane. Jangmi looked on a satellite image like a sloppy, broad, somewhat disorganized storm. The kind of storm that experienced Japanese residents had ridden out in their homes many times before. What the satellite image could not show was the relationship between that broad rainfall footprint and the geography it was about to pass over. Japan is a mountainous country with thousands of short, steep river systems that drain quickly into the Pacific. When rain falls heavily over the mountains, it does not pool. It runs. Down narrow valleys, through forested slopes into rivers that can rise from ankle-deep to roof height in a matter of hours. That is the geography Jangmi was about to cross. The warning system fired where it was supposed to fire. The rivers rose exactly the way the instruments said they would. What the system could not control was the rain that produced all of it. And those numbers are the part of this story that nobody put in the headline. 5 days old, and it was already being tested for real. The new system fired at its two highest levels simultaneously across multiple river systems on day 5 of its existence. And the question nobody can answer yet is this. What is it designed to do on the day it needs to fire everywhere at once? The instruments that produced those warnings were not guessing. They were responding to rainfall numbers that had already broken records before most of the country had woken up. And those rainfall numbers are where this story shifts from a question about a warning system to a question about water. In the 24 hours through 4:50 p.m. on Tuesday, June 2nd, a rain gauge in the town of Tano in Miyazaki Prefecture recorded 304.5 millimeters of rain. That is the highest June total ever recorded at that location. Not the highest in recent memory. The highest ever since records at that gauge began. To put 304.5 millimeters into terms that an American viewer can hold in their hands, that is just shy of 12 inches of rain. 12 inches in 24 hours. A foot of water falling from the sky onto a single point in one calendar day. The average rainfall for Tano in the entire month of June is far less than that. The gauge recorded an entire month's worth of normal June rain, and then some more, in a single 24-hour stretch. The Japan Meteorological Agency keeps these records going back decades. Some of the rainfall stations in Miyazaki have been operating continuously since the 1970s. The 304.5 number broke a record that had stood for the lifetime of every adult living in that town. Local officials at the Miyazaki Regional Meteorological Office confirmed it on the morning of June 3rd. The number was not an estimate. It was not a projection. It was a measurement taken on the ground by an instrument designed for that exact purpose. What the headline said was that Jangmi caused heavy rain in southwestern Japan. What the data said was that Jangmi had already produced a 24-hour rainfall total that had never been seen at that location in any June, in any year, in the history of the gauge. Across the border in Wakayama Prefecture, the numbers were worse on a per-hour basis. In the Nishikawa district of Kanagawa, 300.5 millimeters of rain fell in the 12 hours through 4:30 a.m. on June 3rd. That is 11.8 inches of rain in half a day, twice the rate of the Tano record. The water did not have time to soak into the ground or drain through the river system. It pooled. It rushed downhill. It hit the Koza River as a concentrated wall of water that the river could not absorb. That is why the Koza overflowed at 5:35 a.m. That is why the level 5 warning fired when it did. In my prefecture, the rainfall pattern was different, but the cumulative effect was the same. Several areas in the prefecture recorded daily rainfall totals equivalent to an entire month's worth of precipitation. One day, 1 month's worth of water. For the rain gauges that recorded those numbers, June 2nd was effectively a year-compressing event. The water that was supposed to fall across 30 days fell in 24 hours. Here's what those numbers actually mean for the people who live underneath them. A flat-roofed house in the United States is typically engineered to handle a maximum sustained rainfall rate of about 4 to 6 inches per hour. Above that, gutters cannot keep up, drain pipes back up, and water begins to pool against foundations and walls. The Kanagawa rate of 300 millimeters in 12 hours works out to roughly 1 inch per hour on average, but the actual distribution was concentrated. Peak hourly rates during the heaviest bands likely approached or exceeded the design tolerances of residential drainage infrastructure. That is when houses start taking on water. That is when basements flood. That is when retaining walls fail. The Japan Meteorological Agency had warned before the storm even arrived that something unusual was going to happen with the rainfall. They had identified a stationary weather front sitting north of Jangmi. A stationary front, in plain English, is a boundary between two air masses that has stopped moving. Warm, moist air on one side. Cooler, drier air on the other. When a typhoon pushes moist, tropical air northward into a stationary front, the moisture has nowhere to go. It rises, it cools, it condenses. It falls as rain. The result is heavy rainfall that lands on the ground before the storm center even arrives. That is what happened on June 1st and June 2nd. The ground across southwestern Japan was already wet before Jangmi made landfall. The stationary front did the first round of soaking, then the storm arrived and did the second. Here's what that actually means. A kitchen sponge sitting on a wet counter. Normally, a sponge can absorb a significant amount of water. You can pour a cup of water on a dry sponge and the sponge drinks it up. The cup disappears into the foam, but if the sponge is already fully saturated, already soaked through, the next cup of water you pour does not absorb at all. It runs straight off the sponge. It pools on the counter. It goes wherever gravity takes it. That is what a stationary front does to the ground before a typhoon arrives. The soil is the sponge. The front fills it first, and then the storm pours the next cup on top. By the time the heaviest rainfall bands hit, the ground has lost the ability to soak up water. Every drop runs downhill. Every drop ends up in a river that is already at capacity. And the rainfall came in bands. Not one even sheet of rain spread across the whole storm, but several separate, intense rainfall corridors that formed independently and stacked on top of each other in time. The Japan Meteorological Agency identified linear precipitation zones in southern Wakayama, in southern Tokushima, on the Izu Peninsula in Shizuoka, and in eastern Kanagawa. These are not all in the same place. Southern Wakayama is on the southern coast of the main Japanese island. Tokushima is on the island of Shikoku. The Izu Peninsula is to the east, jutting into the Pacific just south of Tokyo. Eastern Kanagawa is the suburban zone around Yokohama. These four locations are spread across hundreds of miles of coastline. All of them experienced rainfall intensification at the same time. A linear precipitation zone is what meteorologists call a band of very heavy rain that forms along a narrow line, sometimes only a few miles wide but tens of miles long. Once a linear precipitation zone sets up, it can dump enormous amounts of rain on the same strip of geography for hours. The zones that formed during Jangmi were each capable of producing rainfall rates that, by themselves, would have justified a level 4 warning. The fact that 4 of them were active simultaneously in 4 different prefectures was what pushed the warning system into territory it had never been designed to handle on its first week of operation. The data tells a different story than the headline. Several major outlets noted accurately that Jangmi had weakened from typhoon to tropical storm status by the time it reached the main Japanese island of Honshu. That is technically true. The sustained wind speed had dropped below the threshold for typhoon classification. But wind classification does not determine flood risk. A weakened tropical storm with 126 kilometers per hour, winds at the surface still produced record June rainfall at multiple gauges. It still activated both level 4 and level 5 warnings. It still pushed river levels into emergency territory. The storm's category on the Saffir-Simpson scale had almost nothing to do with what happened on the ground. What the broad-eye Scott Braun's team had identified at NASA Goddard 3 days earlier did determine was the total rainfall footprint. A wider eye spreads the rainfall across more area. A weaker but broader storm can produce a larger total volume of rain than a stronger, more compact storm because the heaviest rainfall band covers more square miles. Jangmi was that kind of storm, less intense at any single point, more dangerous across the whole footprint. The rivers responded the way the rainfall numbers said they would. By 5 a.m. on June 3rd, the Koza River in Wakayama had overflowed at Tsukunos. By dawn, the Komozu and Komozu Furukawa in Sioux City had triggered level 4. By mid-morning, the Tatagawa River in Tokyo's Shinagawa ward had crossed the threshold to trigger Tokyo's first-ever level 4 alert. Each of these activations was a direct response to rainfall numbers that had been measured upstream in the previous 12 hours. The instruments were not predicting. They were reporting on water that had already fallen and was already moving downhill. In Tokyo, the rainfall numbers were smaller in absolute terms than what fell in Wakayama or Miyazaki. The Tokyo metropolitan area received roughly 100 to 150 millimeters across the worst affected zones over the course of June 2nd and June 3rd. That is about 4 to 6 inches of rain. By Wakayama's standards, that is moderate. By Tokyo's standards, on top of already wet ground from the stationary front, it was enough to push the city's rivers into the new alert framework's danger thresholds for the first time. The Tatagawa River runs through Shinagawa Ward. The Zenpakuji runs through Suganami Ward. The Kanda runs through central Tokyo. The Meguro runs along the southern edge of the central wards. The Nogawa flows on the western edge of the metropolitan area. These rivers are some of the most monitored waterways in the world. They are lined with concrete embankments, walled with floodgates drained by underground reservoirs the size of cathedrals. Tokyo has spent billions of yen building infrastructure specifically designed to keep these rivers in their channels during heavy rain. On June 3rd, that infrastructure was tested. It held. But the warning system fired anyway because the river levels themselves had reached the trigger threshold. In Ome City, on the western edge of Tokyo, The rainfall produced a secondary effect that the warning system did not capture in its alerts. The water supply infrastructure that serves the city was damaged or contaminated. By the end of June 3rd, 1,800 households in Ome were without running water. Tokyo Electric Power Company reported that more than 12,000 homes in the Kanto-Koshin region had lost electrical power. The flooding had taken out roads, including a section of National Highway in Ota Ward. None of these consequences were the wind. All of them were the water. The rainfall numbers explain how the rivers rose. They do not explain what happened when the warnings went out. And that is where this story takes its sharpest turn. 1 month of rain. 1 day. That is what the gauge said. If a storm that had already weakened past typhoon status still produced record-breaking June rainfall across 5 separate regions at the same time, what does a full-strength storm on the same track do to ground that is already this wet? The rainfall numbers explain why the warnings fired. They do not explain why so few people responded to them. And that is the part of this story that everyone in Japan is now trying to understand. Reporters from Japanese broadcasters and wire services fanned out across the Tokyo metropolitan area on the morning of June 3rd. Their assignment was simple: visit the evacuation centers and document what was happening inside them. The Level 4 danger warning had been issued to over 1.6 million residents across Tokyo, Kanagawa, and Chiba. Shelters had been opened in dozens of wards. The instruction from the Japanese government was clear. If you are in an affected zone, leave. Go to your designated shelter. Do not wait. A reporter from one of Japan's major broadcasters arrived at a voluntary evacuation center in Shinagawa Ward shortly after dawn. The center was inside a public school gymnasium. The lights were on. The cots had been set up. Bottled water had been stacked along one wall. The ward staff who had opened the facility were sitting at a folding table near the entrance, waiting to register residents and direct them to their assigned spaces. There were no residents. The reporter walked through the gymnasium and counted. 0 evacuees. The ward staff confirmed it. They had opened the facility several hours earlier. One resident had come in briefly. That resident had looked around, decided they did not need to stay, and had gone home. That was the total count. One person briefly returning home. The shelter was otherwise completely empty. Shinagawa Ward had received Tokyo's first-ever Level 4 heavy rain danger alert that morning. The Tadagawa River, which runs through the ward, had risen to the threshold that triggered the new warning category. Evacuation orders had been issued across the entire ward. The estimated population under evacuation order in Shinagawa alone was in the hundreds of thousands. The shelter the reporter visited served a substantial residential area within walking distance. One person had used it, and they had left. The same pattern repeated across the Tokyo metropolitan area. Reporters from different outlets visited shelters in different wards and found similar conditions. Almost no one was coming in. The evacuation orders had reached over 1.6 million phones. The Level 4 danger warnings had sounded the loud emergency alert tone in apartments and houses across 3 prefectures, and the shelters were largely empty. The cause of the non-compliance is not a single thing. It is a stack of overlapping reasons that produce the same result. The first reason is the wording of the warnings themselves. The Shinagawa Ward evacuation guidance, like the guidance issued by many other municipalities, made a distinction between residents in dangerous locations and residents in safe locations. People in dangerous locations were told to evacuate immediately. People in safe locations were told they did not need to move to a designated shelter. The problem was that many residents had no clear sense of which category they fell into. If you live on the second floor of a sturdy apartment building 2 blocks from the river, are you in a dangerous location or a safe location? The official answer depends on the specific elevation of your floor, the construction of your building, and the projected flood depth in your specific block. Residents do not have that information at their fingertips at 5 a.m. when an emergency alert is going off on their phone. They have to make a judgment call, and on June 3rd, hundreds of thousands of residents in Tokyo made the same judgment. They decided they were probably in the safe category. They stayed home. The second reason was the calibration of the storm itself. Jangmi had been described in the days leading up to landfall as a weakening system. The category had been downgraded from typhoon to tropical storm before it reached Honshu. The wind speed numbers, while elevated, were not catastrophic. Tokyo residents who had lived through previous typhoons knew what a serious storm felt like, and many of them concluded that Jangmi did not feel like one. The rain was heavy but not unprecedented in the city itself. The wind was strong but not destructive. From inside a typical Tokyo apartment, the storm sounded ordinary. The third reason was something deeper. Japan has been experiencing what disaster researchers call alert fatigue. Over the past decade, the country has issued increasingly frequent and increasingly strongly worded warnings about typhoons, heavy rain, earthquakes, and landslides. In many cases, the warnings have been technically correct, but the predicted disasters have not fully materialized in the areas where most people live. Each near miss reduces the perceived urgency of the next warning. By June 2026, many Tokyo residents had received dozens of emergency alerts over the years. The new Level 4 was, to them, just another alert in a long series. Except it was not. It was specifically designed to mean something different than every alert that had come before it. Takahiko Yamamura is an expert at the Disaster Reduction and Human Renovation Institution in Japan. After the storm, he issued a public assessment of what had happened. His statement, translated into plain English, was this: because there was no major flooding and relatively little damage, most people did not evacuate. If people ignore future danger alerts, they may fail to evacuate when a truly life-threatening situation occurs. What Yamamura was actually saying underneath the careful institutional language was something blunter. The first activation of the new warning system created a learning experience for the Tokyo population, and the lesson they learned was the wrong one. They learned that they could ignore the warning and be fine. They learned that staying home was safe. They learned, in effect, that the Level 4 danger warning was not actually a danger warning in any meaningful sense. What the data shows that Yamamura did not say out loud was this: the next storm that prompts a Level 4 warning in Tokyo will face a population whose first lived experience with that alert was a non-event. That is not a hypothetical concern. That is a measured behavioral baseline that has now been established. The credibility of the new system, in Tokyo specifically, took a hit on its first day of operation that may take years of repeated correct activations to repair. The pattern documented during Jangmi is not new. It mirrors the behavioral pattern that researchers have documented in the lead-up to fatal storms in Japan's past. Japan's post-Hagibis casualty reviews from 2019 consistently found that the majority of deaths occurred in areas under evacuation orders where residents chose not to leave. The 2018 Western Japan floods produced a similar pattern. The 2020 Kyushu floods produced a similar pattern. In each case, residents in known danger zones who had received specific evacuation instructions decided to stay. Some of them died, most of them did not. The ones who survived the near misses became part of the population that, in the next storm, was even less likely to evacuate. The new Level 4 danger warning system was specifically designed to break this cycle. The entire purpose of carving out a distinct level above general advisories was to give Japanese authorities a clear, unambiguous tool to say, this is the one. This time, you actually need to leave. The system was supposed to be reserved for the moments when evacuation was the difference between life and death. On its first activation, it was issued correctly. The rainfall numbers justified it. The river levels supported it. The storm was real. But the consequences in the affected zones did not match the urgency of the warning. The river levels in Tokyo went up, threatened, and went back down. Houses got wet but did not float away. Roads flooded but were drained within hours. The disaster that the Level 4 warning was forecasting did not arrive in Tokyo in the way it had been suggested. That is the worst possible outcome for a brand new life safety system. Not failure. Not catastrophe. A correct warning followed by a manageable event. Because that is the combination that teaches a population that the warning does not mean what it says. There is a researcher named Susan Cutter at the University of South Carolina who has studied evacuation behavior in the United States for decades. Her work on hurricane evacuation along the Gulf Coast and the Atlantic Coast has produced a finding that maps directly onto what happened in Tokyo on June 3rd. Cutter's research shows that the strongest predictor of whether someone will evacuate during an upcoming storm is whether they evacuated during the last storm and felt that the evacuation was worth it. If they evacuated and the storm was bad, they will evacuate again. If they evacuated and the storm was mild, they are less likely to evacuate next time. If they did not evacuate and the storm was mild, they are dramatically less likely to evacuate next time. The Tokyo population on June 3rd was in the third category. They did not evacuate, and the storm was, from inside their apartments, mild. The behavioral imprint that left is the imprint Cutter's research predicts will reduce evacuation rates in the next storm. This is the part nobody is watching closely. Everyone is watching the storm damage, which was real but limited. The compliance failure was not damage in the traditional sense. It did not show up in the casualty count. It did not produce destroyed homes. It produced something that does not show up on any map, a shift in the relationship between the Japanese government and the people it is trying to protect. The 1.6 million residents who received the Level 4 warning and did not move have now collectively written the first chapter of how Japan responds to its new warning system. The next storm will arrive with the same warning, sent to many of the same phones in many of the same neighborhoods. The people who stayed home on June 3rd will be the people deciding again whether to leave or stay. What most coverage did not mention was that the compliance failure on June 3rd was not a Japanese cultural problem or a Tokyo-specific issue. It is a universal pattern in disaster response. The same dynamic plays out in Florida before hurricanes, in California before wildfires, in New Orleans before storms approaching the Gulf. The same dynamic plays out everywhere that life safety warnings are issued to large populations. Japan's situation is distinctive because the system that was tested is brand new. The warning was the first activation, and the population's response was documented in real time by reporters who happened to be standing in empty shelters. That documentation matters. Future disaster response researchers will study the June 3rd evacuation rates the way disaster historians study the lead-up to Hurricane Katrina. The data is now baseline. The pattern is now measured. The next storm will face a population whose response to Level 4 has been observed and recorded. The question of why people did not move is partly about this storm. It is mostly about what happens the next time the same warning goes out, in the same city, to the same people who stayed home and found out nothing bad happened to them. 1.6 million warnings sent. One person showed up? One. The warning was issued. The shelters were ready. The storm passed without mass casualties in Tokyo. And the question nobody can answer is whether the next city that gets this warning, after Tokyo survived by staying put, will move at all. The compliance question is one part of the story. The other part is the question of whether June storms threatening Tokyo are supposed to be happening at all. Because what the historical record shows is that they are not. Japan's typhoon season has a shape that is reliable enough to put on a calendar. The Japan Meteorological Agency tracks typhoon activity going back to 1951. The average season produces roughly 26 named storms in the Northwest Pacific Basin between January and December. Of those 26, only about 3 per year directly cross over the Japanese archipelago. The rest stay offshore, curve away into the open Pacific, or weaken before reaching Japan. That average masks a very strong seasonal pattern. The peak months for typhoon landfalls in Japan are August and September. By late summer, sea surface temperatures in the western Pacific have reached their annual high. The atmospheric conditions are most favorable for tropical cyclone development. The storms that do form during these months are larger, more organized, and more likely to track north toward Japan. October still produces significant typhoons, but the frequency starts to decline. By November, landfalls become rare. By December, almost unheard of. The other end of the season is supposed to be even quieter. Tropical cyclone activity in the Northwest Pacific historically picks up slowly through the spring. April typhoons are uncommon. May typhoons are uncommon. June typhoons are uncommon. The conditions necessary for a typhoon to form, organize, and track north to Japan in early June are not typically present. The ocean is still warming. The atmospheric patterns are still transitioning out of winter. The systems that do form usually weaken or veer away before reaching land. That is the historical baseline. That is what the calendar is supposed to look like. Typhoon Guchul in June 2012 was the first typhoon to make landfall in Japan in the month of June since 2004. That is an 8-year gap between June landfalls. Before Guchul, the previous June landfall in 2004 had itself been treated as unusual. The pattern across the second half of the 20th century was clear. June was not typhoon month. Storms might form in June, but they were not supposed to threaten the main Japanese islands. Jangmi arrived in early June 2026, 14 years after Guchul, but the gap between June landfalls is no longer 8 years. It is shrinking. And the storms that are making it through in June are not minor systems. Jangmi triggered the first ever activation of both Level 4 and Level 5 warnings under Japan's new framework. That is not a minor system. That is a system serious enough to test the country's brand new national life safety architecture. The question of why this is happening points to a number that has been measured for decades and is no longer behaving the way it used to. Sea surface temperature, tropical cyclones including typhoons, hurricanes, and cyclones in the Indian Ocean are heat engines. They need warm ocean water to form and survive. The threshold below which a tropical cyclone cannot sustain itself is generally accepted as 26.5 degrees Celsius. Below that temperature, the warm, moist air that fuels the storm's circulation cannot rise fast enough. The storm loses its energy source. It weakens and falls apart. The 26.5-degree threshold is a hard floor. Above it, storms can form and sustain themselves. Below it, they cannot. The shape of the world's tropical cyclone zones is essentially the shape of where ocean surface temperatures spend enough of the year above 26.5 degrees to support storm development. That shape used to be more or less stable. The Western Pacific warm pool was a known geography. The Atlantic main development region was a known geography. The storms moved within those zones in patterns that had been studied for 100 years. Now those zones are expanding. The 26.5-degree water is reaching further north than it used to. It is reaching higher latitudes earlier in the year and staying at higher latitudes later in the year. The total surface area of ocean warm enough to support tropical cyclone development is larger than it was in the 1970s. The window of time when that water can fuel storms is wider. Western Pacific sea surface temperatures during Jangmi's formation, in late May and early June 2026, measured 29 to 30 degrees Celsius across the storm's track. That is nearly 3 degrees Celsius above the formation threshold. That is the difference between water that can barely sustain a storm and water that can rapidly intensify a storm. Jangmi was forming and traveling through ocean that was, by tropical cyclone standards, hot. Here is what that means. A typhoon needs warm ocean water to stay alive as it moves north. Below a certain temperature, it falls apart. Think of it like this: a campfire. As long as you keep feeding it dry wood, it burns. It does not matter how far from the original lighter you are, the fire keeps going. Take away the wood or drench it with cold water, and the fire goes out, no matter how hot it was burning before. That is what sea surface temperature is to a typhoon. Warm water is the wood. When the ocean stays warm far north of where it used to, the fire keeps burning. Further up the coast, later in the year, earlier in the year, and closer to Tokyo. There is a specific ocean current that runs along Japan's Pacific coast called the Kuroshio. It is one of the largest warm water currents in the world, comparable to the Gulf Stream in the Atlantic. The Kuroshio flows north from the tropics, carrying warm equatorial water up the eastern edge of the Japanese archipelago. It then turns east and crosses the Pacific toward North America. The current has been measured continuously for decades. It is, by any measurement, warmer than it used to be. What that means in practical terms is that the warm water highway that runs along Japan's Pacific coast is delivering more heat further north than it did 50 years ago. Storms that form in the warm pool of the Western Pacific can ride that warmer current northward and stay organized longer than they used to. Storms that in 1975 would have weakened and dissipated before reaching Honshu can now hold together long enough to make landfall. That is the underlying mechanism behind the shrinking gap between June landfalls. The water that storms need to survive is reaching further north earlier in the year. The number of viable June storm tracks toward Japan has grown. The probability of a Tokyo-threatening typhoon in early June has gone from near zero in the 1980s to a measured non-zero number in the 2020s. Typhoon Sinlaku in April 2026 was the other data point that bookends this season. Sinlaku formed in early April and rapidly intensified into a super typhoon with sustained winds of 175 miles per hour. It caused extensive damage across Saipan and the northern Mariana Islands. It became the first April typhoon since Typhoon Malacus in 2022. It became the strongest storm anywhere on Earth so far in 2026. April super typhoons are historically rare. The conditions that would allow a tropical cyclone to reach Category 5 strength in April are typically not present in the Northwest Pacific that early in the year. Sinlaku formed and intensified anyway, and the same warm sea surface conditions that allowed Sinlaku to do that in April were still in place in late May when Jangmi formed. Two storms in the same season, both arriving outside their historical windows. Sinlaku in April, Jangmi in June. The 2026 Pacific typhoon season has now produced two anomalously early, anomalously powerful storms before the statistical peak months of August and September have even begun. This is what makes Jangmi a different kind of story than a single weather event. A single storm in June would be a curiosity. Two storms outside their windows in the same season is a pattern, and the pattern is consistent with what climate researchers have been predicting for 2 decades. Warmer oceans, expanded storm zones, longer active seasons, earlier arriving storms. The 2026 season is showing all of those signatures. What most coverage did not mention was that the same warm Pacific sea surface temperatures fueling Jangmi are part of a globally connected pattern. The Atlantic hurricane season opened officially on June 1, 2026, 2 days before Jangmi made landfall. Forecasters at NOAA's National Hurricane Center were already monitoring the Atlantic basin's developing conditions. Some of the same warm water signatures present in the Pacific are also present in the Atlantic main development region. The Walker circulation, which is the broad east-west atmospheric pattern that links the two oceans, is in a configuration that researchers associate with more active Atlantic hurricane seasons. This is not a forced connection. Warm Pacific sea surface temperatures and Atlantic hurricane season intensity share a documented correlation through the Walker circulation. When the Pacific is warm in the pattern it is currently in, the Atlantic tends to be more active. Both basins are now simultaneously in active threat windows. The forecasters at the National Hurricane Center said as much in their May seasonal outlook, before Jangmi had even formed. They projected an above-average 2026 Atlantic hurricane season. The ocean heat content in the Atlantic main development region was running well above the 1991 to 2020 climatological average. Wind shear in the Atlantic was forecast to remain low to moderate, which is favorable for storm development. The combination, in the language of the outlook, was conducive to an active season. That outlook is now being tested against a Pacific season that is already running ahead of its historical pace. Both oceans are warm. Both seasons are open. Both basins have produced early activity. The pattern is consistent. The historical comparison that frames Jangmi most clearly is not another Japanese typhoon. It is the relationship between what used to be normal in June and what is now happening in June. Typhoon Guchul in 2012 was the only June typhoon to make Japanese landfall in the previous 8 years. Jangmi in 2026 represents a continuation of a trend in which June landfalls are not unprecedented anymore. They are starting to be expected. If the typhoon season can now produce a Tokyo-threatening storm in June, it can produce another one in July, and another one in August, and another one in September, and another one in October. The season just got longer at the front end without getting shorter at the back end. The same population now faces a wider window of risk than the historical pattern suggested. What most coverage did not mention was that this lengthening is not abstract. It has a price. Every additional month of active typhoon risk is another month during which warnings might be issued, during which evacuations might be ordered, during which the new Level 4 and Level 5 framework might fire. Each activation either reinforces the credibility of the system or, as on June 3rd, accidentally erodes it. A longer season is also a longer test of the system's ability to maintain public trust over many activations. The ocean is warmer than it used to be this far north. The storms are arriving earlier than they used to. And somewhere in the gap between those two facts is a small town in Wakayama Prefecture, where the road out of town was already gone before most people even woke up. The gap between June typhoons used to be 8 years. Now it is something else. Here is the open loop. The water along Japan's Pacific coast is warm enough to sustain a typhoon in early June. The storms are arriving in months they did not used to arrive. And the question is, how many June warnings does Tokyo receive before this stops being treated as a statistical anomaly and starts being treated as the new shape of the season? The shape of the season is one thing. The shape of what happened in a single small town in Wakayama Prefecture is another. And it is in that town, in the hours before dawn on June 3rd, that the cost of Jangmi was paid in the most concrete way. Kozagawa is not a large place. It is a town of roughly 2,200 people, sitting in a valley along the lower stretch of the Koza River, in the southern part of Wakayama Prefecture. The town is rural by Japanese standards. The economy is built around forestry, fishing, and small-scale agriculture. The main road that connects the town to the outside world is National Route 371, a 2-lane highway that runs alongside the river and threads through the mountains toward the cities further north. There is one road in and one road out. That is the geographic fact that mattered on June 3rd. At 5:35 in the morning, the Japan Meteorological Agency issued the first Level 5 emergency flood warning ever under the country's new national system. The warning was for the Koza River. The river had already overflowed. Water was moving into houses in the Sukuno's district of Kozagawa. The Level 5 designation does not mean leave. It means it may already be too late to leave. The instruction at Level 5 is to find the highest floor of the strongest building you can reach and stay there. The director of forecasting at the Japan Meteorological Agency in Tokyo, addressing the situation in Kozagawa, said in a public statement, "Please evacuate to safer places than where you are now because your lives are in danger." Those were not bureaucratic words. They were not metaphorical. They were a senior government meteorologist telling the residents of a specific town, by name, that their lives were in danger at that moment. For some of those residents, the option to leave the town entirely had already been removed. A section of National Route 371 running along the river collapsed during the peak of the flood. The road broke, not in some minor way. A whole section gave way under the combined weight of the saturated hillside above it and the floodwater below it. The highway that served as the primary evacuation route out of Kozagawa was, by daylight, no longer there. That is the situation the residents of Kozagawa woke up to. Their river was at Level 5, their road was gone. Their highest national life safety warning was telling them not to try to travel. There was no path out. In the neighboring town of Kushimoto, the situation was somewhat less severe, but the warning was the same. Both Kozagawa and Kushimoto were under what Japan calls an Emergency Safety Secured Order, which is the highest evacuation designation the country issues. In Kushimoto, that order covered 755 households and 1,049 people. In Kozagawa, it covered 862 households and 1,072 people. Together, that is just under 2,800 people, directly under the highest emergency designation Japan can issue. These were not anonymous statistical aggregates. These were specific neighborhoods. Specific streets, houses where families were sleeping when the alarm tone went off on their phones. The Tsukunos district of Kozagawa, where the river overflowed first, is a small cluster of homes along the riverbank. The streets are narrow. The houses are mostly 2-story wooden structures with terracotta tile roofs, the kind of construction common in rural Japan. They are designed to handle earthquakes. They are not designed to handle 11 inches of rain in 12 hours on already saturated ground. The Koza River overflowed before sunrise. By the time the first daylight came over the mountains, water was already standing in living rooms in Tsukunozu. Some houses took on enough water to render the ground floor uninhabitable. Furniture was destroyed. Appliances were ruined. personal belongings stored at floor level were soaked. The cleanup for the families affected will run into weeks. The replacement of damaged property for households without flood insurance will be a long-term financial burden. The Level 5 warning after several hours was downgraded to Level 2 as the river receded. That downgrade did not put the road back. As of the morning of June 4th, more than 24 hours after the worst of the flooding, National Route 371 was still collapsed. Crews were working to assess the damage and begin repairs, but the highway was impassable. Residents of Kanagawa and Kushimoto who needed to travel north toward the regional hospitals, the larger commercial centers, or the train stations connecting to the rest of Japan could not get there by road. There is a researcher named Hiroshi Inoue at Kyoto University who has studied evacuation geography in rural Japanese towns for the past decade. Inoue's published work, available through the Disaster Prevention Research Institute, focuses on what he calls evacuation route singularity, the condition in which a town has only one practical way out. When that route is compromised, the town becomes effectively isolated, and the only safe option is to shelter in place. Kanagawa is a textbook example of evacuation route singularity. The town sits in a river valley. The river runs along the highway. When the river floods, the highway floods. When the highway breaks, the town's only road out is broken. There is no parallel route. There is no alternative. What Inoue's research has documented is that towns with evacuation route singularity have higher rates of casualties during flood events than towns with multiple egress paths. The reason is straightforward. If the only road floods, people who waited too long to leave have no second chance. If you live in a town with two roads out and one floods, you can still take the other one. If you live in a town with one road out and it floods, you are stuck. Kanagawa on June 3rd had no road out. The residents of the affected districts could not have evacuated even if they had tried. The Level 5 warning's instruction to shelter in place was the only option they had. That is the actual situation that the new warning system was facing on its first day in the field. Not a city of 37 million people deciding whether to walk to a shelter, but a small town of 2,800 people in a river valley with no road out and a river that had already overflowed. The Level 5 designation for those residents was not a warning. It was a description of conditions they were already living through. What most coverage did not mention was that the residents of Kanagawa and Kushimoto, in their official numbers, are exactly the population that Japan's disaster planning has been most worried about. The country's rural prefectures are aging. The population of small coastal towns has been declining for decades as young people move to cities. The residents who remain are disproportionately elderly. Many of them live alone or with elderly partners. Many of them have mobility limitations that make rapid evacuation difficult under the best conditions. In Kushimoto, the median age of the population is over 60. In Kanagawa, it is similar. These are not towns of young, healthy adults who can hike to higher ground if the road floods. These are towns where the typical resident is more likely than not to have arthritis, reduced eyesight, or a chronic condition that requires regular medication. The Level 5 warning's instruction to find the highest floor of a sturdy building is a reasonable instruction for an able-bodied adult. It is a much harder instruction for an 82-year-old woman living alone in a two-story house with a ground-floor bedroom. The Fire and Disaster Management Agency tracked injuries across the affected prefectures on June 3rd and the days following. The final count, as of June 4th, was at least 23 people injured nationwide as a result of the storm. 57 houses were damaged. No mass casualty events were reported. By the standards of catastrophic typhoons, those numbers are remarkably low. That is the part that needs to be held carefully. Jangmi was, in terms of human casualties, a manageable event. The infrastructure mostly held. The injuries were mostly minor. The deaths in the immediate aftermath were avoided. By any traditional measure of disaster severity, Japan came through Jangmi well. But the way Japan came through it was through a specific combination of luck and circumstance. The storm weakened before reaching the main population centers. The compliance failure in Tokyo did not lead to mass casualties because the floodwaters did not reach the homes of the people who stayed. The collapsed highway in Kosagawa did not strand evacuees in the open because the residents of Tsukinoshi had already either left or had decided to shelter in place. The casualty numbers were low because the worst-case scenarios did not materialize, not because the warning system or the population's response succeeded. That is the harder lesson. The Level 5 warning in Kosagawa was issued correctly. It described the conditions accurately. The residents had no road out and could not have evacuated even if they had wanted to. The fact that no mass casualty event occurred in Kosagawa is not evidence that the system worked. It is evidence that the geography happened to be forgiving in this particular instance. There is a phrase in disaster research called narrow miss outcomes. A narrow miss is an event that produces minimal harm, despite conditions that easily could have produced severe harm. Researchers who study narrow miss outcomes warn that they are dangerous in a specific way. They teach the wrong lesson. They suggest that the system can handle conditions like these. They obscure the fact that the actual harm avoidance was the result of factors outside the system's design. Kosagawa on June 3rd was a narrow miss. The river overflowed. The road collapsed. The Level 5 warning fired, and nobody died. The reason nobody died was not that the warning system protected the residents in any active sense. It was that the residents who were in the worst affected districts happened to be on upper floors when the water came, or happened to have already moved to safer locations during the previous evening, or happened to live in houses that the floodwater did not reach, despite the river being out of its banks. The road out of Kosagawa is still down. The river that put it there is at level 2 and falling. But the same storm system that did all of this, the system that fired both a level 4 and a level 5 warning on its 5th day of operation, was not the most dangerous storm Japan has seen in recent memory. It was not even close. Nowhere to go. The road was already gone. The Koza River returned to level 2 within hours. The highway that was supposed to be the way out is still collapsed. And the question nobody can answer yet is, when the next storm comes and the same river rises again, what exactly do the 1,600 people in those two towns do? The collapsed highway in Kosagawa was one corner of Japan's geography during Jangmi. There was another corner, one that received almost no coverage in Western media, where the stakes were larger than they were given credit for. That corner was Yokosuka. Yokosuka sits on the western edge of Tokyo Bay, about 40 miles south of central Tokyo. It is a Japanese city of roughly 380,000 residents, but its actual strategic significance is something else entirely. Yokosuka is home to Fleet Activities Yokosuka, which is the largest United States Navy installation in Japan. It is the forward operating base for the U.S. 7th Fleet. It is the home port of the USS Ronald Reagan Carrier Strike Group. It is, in the language of American military planners, the most important naval installation the United States operates anywhere in the Western Pacific. On the afternoon of June 3rd, the Joint Typhoon Warning Center on Hawaii issued its updated track forecast for Jangmi. The forecast had Jangmi passing 10 miles south-southeast of Yokosuka at approximately 2 p.m. local time. That is the closest point of approach. Not a graze. Not a near miss in the conventional weather forecasting sense. A storm with sustained winds in the tropical storm range, tracking within a few miles of the largest American naval installation outside the continental United States. Fleet activities. Yokosuka, in response to the forecast, remained in tropical cyclone condition of readiness through early Wednesday morning. The Tropical Cyclone Condition of Readiness System is the U.S. Navy's standardized framework for how installations prepare for an incoming tropical cyclone. It runs from Condition 5, which means a tropical cyclone is expected to threaten the area within 96 hours, down to Condition 1, which means destructive winds of 58 miles per hour or greater are expected within 12 hours or already occurring. Yokosuka was at an elevated readiness level throughout the storm's approach. Base schools were closed on Wednesday, June 3rd, as a precaution. Ships in port were secured. Aircraft were either flown out to safer locations or moved into hardened shelters. The Carrier Strike Group, with the Ronald Reagan as its centerpiece, was managed according to the established storm response procedures the Navy uses for any tropical cyclone passing within range of a home port facility. On Okinawa, far to the southwest, the readiness level was higher. American installations there entered tropical cyclone condition of Readiness 1 emergency. That is the highest readiness level in the framework. It means destructive winds of 58 miles per hour or greater are occurring at that moment. The JTWC's track forecast had Jangmi passing 7 miles west of Kadena Air Base, which is the largest U.S. Air Force installation in the Pacific. Kadena Air Base hosts a significant portion of the U.S. Air Force's tactical aircraft in the Western Pacific. The 18th Wing operates F-15 fighters, KC-135 refueling tankers, and a range of other support aircraft. Marine Corps, Air Station Futenma, also on Okinawa, hosts Marine Corps aviation assets including helicopters and tiltrotor aircraft. Both installations were within the wind field of Jangmi as the storm passed. Wind gusts of 80 miles per hour were recorded at Marine Corps Air Station Futenma during the storm. 80 miles per hour is well within the range where unsecured objects become projectiles and structural damage becomes possible. The 18th Wing Public Affairs Office, in a post-storm assessment, reported no injuries to personnel and no significant damage to aircraft or facilities at Kadena. That assessment held despite wind gusts of 80 miles per hour hitting the installation. In the off-base housing areas around Camp Courtney on Okinawa, families experienced power outages and restricted movement. A banyan tree near Gate 2 Street in Okinawa City came down during the storm. Power went out in family housing units. Schools on Okinawa for American military children were closed. Daily life for the thousands of American families stationed on Okinawa was disrupted in concrete, immediate ways. Yokosuka home ports between 7,000 and 11,000 U.S. Navy personnel and their families. The exact number fluctuates with deployment cycles, but the order of magnitude is consistent. On Okinawa, the total U.S. military and dependent population is closer to 50,000 across all branches. Add in the personnel at Yokota Air Base near Tokyo, at Iwakuni Marine Corps Air Station in southern Honshu, and at the smaller installations scattered across the country, and the total American military presence in Japan is on the order of 55,000 to 60,000 service members, plus their dependents. That entire population was inside the wind field of Jangmi on June 3rd to varying degrees. The Tokyo area personnel experienced the same heavy rain and disrupted commute that the Japanese population experienced. The Okinawa personnel experienced the 80-mile-per-hour gusts. The Yokosuka personnel experienced the closest projected pass of the storm itself. This was not reported in Western news as an American story. It was covered in the United States almost entirely as a Japanese weather event. The American military dimension, with tens of thousands of service members and their families inside the storm's path, moved through the American news cycle in essentially no time. The major U.S. broadcast networks, the major U.S. newspapers, the major U.S. wire services gave the storm coverage primarily as a foreign weather story. The fact that a substantial American population was directly affected was treated as a footnote when it was treated at all. Stars and Stripes, the military-focused publication that serves the U.S. Armed Forces, did cover the storm in detail. They reported on the readiness levels, the school closures, the wind speeds at Futenma. But Stars and Stripes is read primarily by military personnel and their families. The general American public watching the evening news on June 3rd did not learn that an American naval base hosting a carrier strike group had been on elevated tropical cyclone readiness all day. This was in the news cycle for about 30 seconds. Typhoon Jangmi passed within 10 miles of America's largest naval base in Japan. It passed within 7 miles of Kadena Air Base on Okinawa. It produced 80-mile-per-hour gusts at a Marine Corps air station. And none of this was framed in American coverage as an American story. The families at Yokosuka, the service members at Futenma, the students whose schools were closed on June 3rd were invisible in the coverage. What the data shows that the coverage did not is that the United States military's presence in Japan operates within a weather environment that is changing. The installations were built in their current locations during the post-war period, when the typhoon climatology was more predictable. Yokosuka was selected as a naval base in the late 1940s in part because Tokyo Bay was sheltered from the worst of the open Pacific weather. Kadena was selected on Okinawa in part because the island's position offered useful operational reach. The climatology that informed those selections was the climatology of the mid-20th century. That climatology is no longer the operating climatology. The same factors that produced an early June typhoon threatening Tokyo are the factors that produced a closer than historical average storm track to Yokosuka and Kadena. The American military's facilities in Japan are inside a weather envelope that is expanding. The frequency with which they will need to enter tropical cyclone condition of readiness is increasing. There is a researcher named Christopher Field at Stanford University who has studied military infrastructure exposure to climate change. Field's published work, available through the National Academies of Sciences, has documented that U.S. military installations worldwide face increasing exposure to weather-related disruptions as a result of changing climate baselines. The Department of Defense itself has published assessments warning that bases in coastal locations, in tropical cyclone zones, and in low-lying areas are facing operational risks that the original site selection did not anticipate. What Field has said in plain English is that the United States military's infrastructure was built for a world that no longer exists. The bases are still there, the personnel are still there, the mission is still there. But the weather around the mission is different than it was when the bases were built. The U.S. Navy's response to Jangmi was, by all accounts, professional and effective. The readiness procedures worked. The ships were secured, the aircraft were protected, the personnel were briefed and prepared. No injuries were reported at Yokosuka. The mission of the 7th Fleet was not significantly disrupted. By the standards of military storm response, the response to Jangmi was a success. The harder question is what happens when the next storm is closer, or stronger, or both. Jangmi passed 10 miles south of Yokosuka. A storm on a slightly different track with the same wind speed could pass directly over the base. A storm at higher intensity on the same track could produce wind gusts that exceed the design tolerances of the buildings, the ship mooring infrastructure, and the aircraft shelters at the installation. The Department of Defense has been studying these scenarios. The Navy has been studying these scenarios. The exact contents of the operational planning documents are classified, but the public-facing assessments are clear that the threat envelope has been expanding. Each year, the climatology shifts further from the baseline the bases were built for. Each year, the probability of a direct strike by a major typhoon increases. Each year, the question of whether the bases need to be hardened further or relocated or replaced with alternative basing arrangements gets a little more pointed. Jangmi was not the storm that forced that question to a head. The storm passed at distance. The damage was minimal. The operational disruption was contained. But Jangmi was a data point. It was an addition to the growing record of close passes, of elevated readiness conditions, of disrupted family routines on American bases in Japan. Each data point makes the underlying trend a little harder to ignore. What most coverage did not mention was that the U.S. military's response to weather threats in Japan is not optional. The 7th Fleet's mission is forward presence in the Western Pacific. The aircraft at Kadena are part of the deterrent posture in the Indo-Pacific region. The personnel and equipment cannot simply be moved out of the way every time a storm approaches without significant operational cost. Each readiness elevation costs flight hours, costs ship preparation time, costs the schedules of thousands of people whose work supports the deterrent mission. The cumulative cost of more frequent storms is real, even if no single storm produces a catastrophic strike. The American military came through Jangmi with no injuries and no significant damage. That is the good news. The harder question is what this storm revealed about how close those installations sit to a threat that is arriving earlier in the year than it used to. Their schools were closed, their power went out, and nobody covered it. Jangmi passed within 10 miles of Yokosuka and within 7 miles of Kadena, produced 80-mile-per-hour gusts at Futenma, and came and went without an American frame around it. Do you think a carrier group 10 miles from a storm's track is a story, or not? The American military's experience of Jangmi was one slice of the broader question of how this storm fits into the historical record. To understand how unusual or how ordinary Jangmi was, the comparison has to be drawn against the storm that everyone in Japan still remembers. The storm that broke the records that Jangmi did not break. The storm that defined what a serious typhoon in Japan looks like in the modern era. That storm is Hagibis, October 2019. Typhoon Hagibis made landfall in Japan on October 12, 2019, in the Izu Peninsula in Shizuoka Prefecture. It then tracked north across the Kanto region, passing through the Tokyo metropolitan area before exiting into the Pacific. At its peak, Hagibis had sustained winds in excess of 200 kilometers per hour, which is roughly 125 miles per hour, equivalent to a Category 3 hurricane on the Saffir-Simpson scale. It was the strongest typhoon to hit Japan in 60 years. The numbers from Hagibis are still the benchmark against which Japan measures every storm that has followed. Damage exceeded 1.8 trillion yen, which is roughly 16 billion US dollars at the exchange rates of the time. That broke Japan's record for non-tsunami water-related natural disasters. Levees failed at 135 locations along 71 different rivers. More than 68,000 homes were flooded. Tens of thousands of people were forced into evacuation centers. The casualty count was just over 100 dead, with many more injured. The recovery from Hagibis took months in many areas and years in some. Nearly 2 weeks after the storm, 22,000 households were still without electrical power, and 133,000 were still without running water. The water restoration timeline was the longest in modern Japanese disaster response. The infrastructure damage was so widespread that the country effectively had to rebuild significant portions of its river and levee system from scratch in some of the hardest-hit prefectures. Hagibis is the storm Japan rebuilt for. The post-Hagibis infrastructure investment was massive. New levees were constructed at the locations where the old levees had failed. Existing levees were raised and reinforced. Underground reservoirs were expanded. Floodgates were upgraded. The river management infrastructure in the Kanto region, in particular, was rebuilt to a design standard based on what Hagibis had produced. The principle behind the rebuild was straightforward. If Hagibis was the worst recent storm, then infrastructure that could survive Hagibis should be sufficient for any plausible future storm. That assumption is now being tested. Jangmi made landfall with sustained winds of 126 kilometers per hour. That is less than two-thirds of Hagibis' peak wind speed. Jangmi was, by any measure, a significantly weaker storm than Hagibis. The Saffir-Simpson scale would have classified Jangmi as a tropical storm, or low-wind Category 1 hurricane. Hagibis would have been classified as a strong Category 3 hurricane. The difference in wind energy between the two storms is roughly a factor of 4. And yet, Jangmi pushed several of the same Tokyo rivers that flooded during Hagibis up to Level 4 danger warning status. The Meguro River, which runs along the southern edge of central Tokyo, the Zenpakuji River, which winds through Suganami Ward, the Nogawa River on the western edge of the metropolitan area, the Kanda River through central Tokyo. All of these waterways received Level 4 warnings during Jangmi. Each of them had been involved in the flooding patterns that contributed to Hagibis' damage in 2019. The post-Hagibis rebuilt infrastructure held during Jangmi. The levees did not fail. The floodgates worked. The underground reservoirs absorbed what they were designed to absorb. The river levels rose into the warning thresholds but did not produce mass flooding of homes in the central Tokyo wards. By the standards of infrastructure performance, the rebuilt system passed its first major test. The harder question is what that test actually proved. Hagibis struck Japan in October. That is the statistical peak of the typhoon season, when the conditions are most favorable for major storms. But October is also after months of Japan's rainy season have already gone into the ground. The ground across the Kanto region in October 2019 was already saturated when Hagibis arrived. The runoff conditions were as severe as they get. Jangmi struck Japan in early June. That is before the heavy rainy season has fully developed. The ground across the Kanto region in early June 2026 was comparatively dry. The runoff conditions were less severe than they would have been in August or September after weeks of rain. Soil moisture readings across the Kanto region in early June were roughly half of what they reach at the Suyu rainy season's peak in late July. That is the part of the comparison that should be sitting in everyone's mind. Jangmi was a much weaker storm than Hagibis. It struck on much drier ground than Hagibis. And it still pushed Tokyo's rivers to level 4. The infrastructure held, but the warning system fired anyway. The implication of that combination is uncomfortable. The rebuilt infrastructure was designed around what Hagibis produced. It was not designed around what a storm of Hagibis' intensity would do to ground that had already been pre-soaked by an earlier June storm in the same season. The compounding effect of multiple storms in a single season, with the first storm soaking the ground and the second storm pouring rain onto already saturated soil, is a scenario that the post-Hagibis rebuild did not explicitly plan for. The 2026 Pacific typhoon season has now produced one early June storm that pushed Tokyo's rivers to level 4. The heavy rainy season, which Japanese meteorologists call the Suyu, typically runs through July. The main typhoon season then runs from August through October. That is roughly 4 months of additional rainfall that will go into the same ground that Jangmi just soaked. Imagine for a moment, what happens if a storm of Hagibis' intensity arrives in October 2026? The same rivers that Jangmi just pushed to level 4 in June are the rivers that will receive the new storm. The ground that Jangmi soaked in June, supplemented by the Suyu through July, supplemented by August and September rainfall, will be at maximum saturation by October. A storm with twice the wind energy of Jangmi, on ground twice as saturated as it was during Jangmi, would produce runoff conditions worse than what produced Hagibis' record flooding. That is the worst-case scenario the rebuilt infrastructure is now sitting against. Not a storm equivalent to Hagibis. A storm equivalent to Hagibis on top of a season that has already produced a Jangmi-equivalent storm earlier in the year. There is a researcher named Yasuhiro Kano at the University of Tokyo's Institute for Industrial Science who has studied flood infrastructure performance under compound rainfall scenarios. Kano's published work, available through the Institute, has documented that flood infrastructure designed to specific single-event standards performs significantly worse when the design event is preceded by a smaller earlier event in the same season. The compounding effect of presaturation is, in some flood models, equivalent to a 30 to 50% increase in the effective intensity of the design storm. What Kano has said in plain English is this: if you design a levee to handle a 100-year storm, and then a 50-year storm hits earlier in the same season, the levee may only be able to handle a 70-year storm by the time the actual design event arrives. The presaturation effectively raises the bar that the infrastructure was designed to meet. The post-Hagibis infrastructure was designed for Hagibis. Jangmi is now in the season's record. The 2026 design event, if one arrives, will be facing infrastructure that has effectively been derated by the earlier storm in the season. That is one part of the historical comparison. The other part is about the rivers themselves and how they have changed. The Meguro, Zenpukuji, and Kanda rivers in Tokyo are heavily managed waterways. They run through dense urban geography with concrete channels, embankments, and floodgates along most of their length. The capacity of these rivers to carry water has been engineered to specific design specifications. When the river levels rise to the warning thresholds, the engineering is being tested at the limits of its design. What the warning system was reporting on June 3rd was that those design limits had been reached. The rivers were not failing. The infrastructure was not collapsing. But the water levels in the channels were at the thresholds that the Level 4 danger warning was specifically designed to flag. That is what the warning meant. The system that was supposed to keep the rivers under control was operating at the edge of its capacity. That edge of capacity operation, during a storm significantly weaker than Hagibis, is the part that should sit heaviest. The infrastructure was not designed to operate at its limits during a moderate storm. It was designed to have margin. The Level 4 warning fired because the margin was used up by a tropical storm with 126 km/h winds. A storm with 200 km/h winds would consume not just the margin, but the design capacity itself. Japan rebuilt and reinforced its river infrastructure after Hagibis. The system held during Jangmi, but Jangmi was a fraction of Hagibis' strength, and it still pushed multiple rivers to level 4 and level 5. What most coverage did not mention was that the post-Hagibis rebuild was completed within the past 5 years in many locations. The new levees are recent. The reinforced floodgates are recent. The infrastructure is in good condition, well-maintained, and operating as designed. The fact that it was pushed to its limits by Jangmi is not a sign of infrastructure failure. It is a sign that the design standard was set against the wrong baseline. The data tells a different story than the rebuild narrative. The post-Hagibis investment was significant. The engineering was world-class. The infrastructure is performing exactly as designed. But the design was based on the climatology that produced Hagibis, and the climatology has continued to shift since 2019. The storms that the new infrastructure is being asked to handle are not the storms it was designed for. The implication of this is straightforward but difficult to act on. The rebuild needs to be rebuilt. The design standard needs to be raised. The infrastructure investment that Japan made after Hagibis is already 6 years later behind the curve. That conclusion is not coming from this video. It is coming from the published work of Japanese flood engineering researchers who have been documenting the inadequacy of the post-Hagibis design standards in academic journals for the past 2 years. The work is technical. It is not easily accessible, but it is in the literature available to anyone who wants to find it. The researchers studying this issue have been clear that the standards established after Hagibis assumed a level of climate stability that the data has not supported. Jangmi is now another data point in their argument. A weaker storm than Hagibis, on drier ground than Hagibis, pushed the rebuilt infrastructure to level 4. That is the data the engineers will be processing for the next several years as they try to determine what the new design standard should be. Jangmi was the 6th storm of the 2026 season. It arrived in June. The historical average says the strongest storms of the year have not started forming yet. What the rest of this season looks like, and what it means for a warning system that just documented its first compliance failure, is the last piece of this story. Weaker storm, same rivers, same level 4 warnings. That is the arithmetic that matters. If a storm at 126 kilometers per hour on early June ground can push Tokyo's rivers to level 4, what does a 200 kilometer per hour storm do in October to those same rivers after 4 months of rain have already gone into the ground? The rivers Jangmi tested are the rivers a future storm will test again. And the future storm is sitting somewhere in the rest of the 2026 Pacific typhoon season, which by any measure is already running ahead of its historical pace. By the time Jangmi made landfall on June 3rd, the 2026 Pacific typhoon season had already generated 6 named storms. That is the number of named storms the basin typically produces by mid-August in an average year. The season had compressed roughly 10 weeks of normal storm formation into 6 weeks of actual storm formation. The pace was running ahead of climatology before the most active months had even begun. The 4th storm of the 2026 season was Typhoon Sinlaku. Sinlaku formed in early April in the warm waters east of the Philippines. The storm intensified over a 48-hour period, transitioning from a tropical storm to a Category 5 equivalent super typhoon. That pace placed Sinlaku among the fastest, intensifying tropical cyclones measured in the western Pacific since satellite records began in 1970. At peak intensity, Sinlaku had sustained winds of 175 miles per hour. That is among the strongest wind speeds ever measured in any tropical cyclone anywhere on Earth in the month of April. The storm tracked west-northwest across the northern Mariana Islands and Guam. The damage on Saipan was extensive. Trees were uprooted across the island. Buildings were damaged by both wind and flying debris. Power infrastructure was knocked out for weeks. The U.S. territory of the Northern Mariana Islands, which is home to roughly 47,000 people, was effectively cut off from normal services for an extended period. Sinlaku became the first April typhoon since Typhoon Malakas in 2022. It also became the strongest storm anywhere in the world so far in 2026. April super typhoons are not impossible by historical standards, but they are rare. The conditions that allow a tropical cyclone to reach Category 5 strength in early April are unusual. They require sea surface temperatures, atmospheric moisture, and low wind shear to all be present simultaneously in the right configuration at a time of year when most of the Pacific is still recovering from winter conditions. That those conditions were present in April 2026 is the foreshadow of why Jangmi was possible in June 2026. The same ocean heat that allowed Sinlaku to intensify rapidly was still present, in modified form 2 months later. The same atmospheric patterns that favored Sinlaku's track were still present. The basin was primed for early storm formation throughout the spring. Jangmi was the sixth named storm. It was not the strongest storm of the season. It was not the most damaging, but it was the storm that struck mainland Japan, that activated the new warning system, and that produced the institutional first that the historical record will remember. Sinlaku struck a sparsely populated U.S. territory in the Pacific. Jangmi struck a metropolis of 37 million people. The historical significance is not symmetrical. The eye of Jangmi at peak intensity was, as NASA's Scott Braun had noted 3 days before landfall, unusually large for a storm of its wind speed. A large eye means the storm's energy is distributed across a wider geographic area. The rainfall footprint is broader. The wind field, while weaker per square mile than a compact storm's wind field, covers more total square mileage. Jangmi was a broad storm. That breadth was part of why it activated warnings across multiple prefectures simultaneously. The western Pacific sea surface temperatures during Jangmi's formation were 29 to 30 degrees Celsius. The atmospheric wind shear at mid-tropospheric levels was low. These are the conditions that favor tropical cyclone organization and intensity maintenance. The fact that Jangmi did not reach Sinlaku-level peak intensity was a function of its specific track and timing, not the underlying ocean and atmospheric conditions. Those conditions could support a much stronger storm if one were to form in similar circumstances later in the season. The Atlantic hurricane season is running parallel to the Pacific season. NOAA's National Hurricane Center officially opened the Atlantic season on June 1, 2026, 2 days before Jangmi made landfall. The Atlantic Basin's preseason outlook called for an above-average season, with elevated ocean heat content in the main development region and atmospheric patterns conducive to storm formation. The forecasters at the National Hurricane Center were tracking conditions that, in their assessment, would support significant Atlantic storm activity throughout the season. The Pacific and Atlantic basins are linked through what meteorologists call the Walker Circulation. The Walker Circulation is the broad east-west atmospheric pattern that connects the tropical Pacific to the tropical Atlantic through the upper atmosphere. When the Pacific is in certain configurations, the Atlantic tends to be more active. When the Pacific is in other configurations, the Atlantic tends to be less active. The current configuration is one of the patterns that favors Atlantic activity. The Pacific is warm, the Atlantic is warm. The atmospheric link between them is set in a direction that allows both basins to produce storms. This is not coincidence. This is documented connection through decades of research. The teleconnections between the basins are well understood, and the current configuration is in the part of the pattern that is associated with active seasons in both oceans simultaneously. What that means in practical terms is that the geography that watched Jangmi develop in the Pacific is sharing ocean heat with the geography that is now watching for storms in the Atlantic. The 2026 season is shaping up to be active on both sides of the world simultaneously. For Japan specifically, the implication is that the months that historically produce the most powerful typhoons have not arrived yet. August, September, and October are the statistical peak. The 2026 season has already produced 2 anomalously early events before reaching those peak months. The remaining months will determine whether the season ends up as a particularly active year on the historical record or as a year that breaks the records that Hagibis set. There is a researcher named Aiko Kondo at the Japan Agency for Marine Earth Science and Technology who has been studying Pacific Basin storm formation patterns for the past 2 decades. Kondo's work, available through the agency's English-language publications, has documented that the 2026 season's early activity is consistent with the patterns that researchers have been forecasting as climate baselines continue to shift. Her assessment in plain English is that the 2026 season is not an outlier. It is what the new baseline looks like. What Kondo has said is that seasons like 2026 used to be considered exceptional. They were the seasons that broke records. They were the seasons that became case studies. Now, she has argued, they are becoming the type of season that should be expected once every 3 to 5 years. The frequency with which the basin produces this kind of early activity is increasing. What the data shows that Kondo did not say out loud is that the increasing frequency of these seasons has implications for the warning system that just had its compliance failure in Tokyo. If active early seasons are becoming routine, the new warning framework will be tested repeatedly. Each activation will either reinforce or erode public trust. The compliance failure on June 3, 2026 was the first data point in what will become a long behavioral record. Japan now has a new warning system. It has a documented compliance failure on that system's fifth day. It has a collapsed evacuation route in Wakayama that has not yet been repaired. It has 1,800 households in Ome that are still without running water, and it has 5 months of active typhoon season remaining as of June 4th. The combination of those facts is the operating environment that Japan is now sitting in. The Philippine Sea and the waters east of Taiwan are the formation zones that produced Jangmi. Those zones remain warm. The sea surface temperatures in those areas have not cooled below the storm formation threshold. The atmospheric conditions that favored Jangmi's development are still present in modified form as of the morning of June 4th. The next storm to form in the western Pacific will, with high probability, come from one of those zones. There is no specific forecast yet for the next storm. The basin produces storms with significant variability in timing. A 2-week pause might occur, or a new storm might form within days. The conditions are favorable, but the specific triggering events are not predictable at the timescales that matter for daily life. What is predictable is that the season will produce more storms. The only questions are when, how strong, and where they will track. The Atlantic Basin is sitting on similar dynamics. The National Hurricane Center will be issuing its standard forecasts and advisories throughout the season. The first Atlantic storm of 2026 will arrive at some point. Whether it arrives in June, July, or August depends on the specific conditions in the basin, but the long-range forecasts suggest activity is more likely than usual. This is the broader picture that Jangmi sits inside: a specific storm in a specific season, in a specific climate baseline that is no longer the baseline it used to be. The institutional first that Jangmi triggered was real. The compliance failure that Jangmi documented was real. The infrastructure stress that Jangmi caused was real. All of those reals are also data points in a pattern that is bigger than any single storm. 6 storms. April through June. The peak months have not started yet. The 2026 Pacific season is running ahead of its historical pace. Japan's new warning system passed its first live test with a documented compliance failure. And the question sitting under all of it is, when the season's strongest storm arrives in August or September or October, does the country that survived Jangmi act differently? Or does it stay home again? Here's what to watch in the next 72 hours and beyond. If you live in Japan or have family there right now, the immediate threat from Jangmi is over. The storm has moved off the Pacific coast and is transitioning into what meteorologists call an extratropical system. That is the term for a tropical cyclone that has merged into the broader weather patterns of the middle latitudes and lost its tropical structure. Jangmi is no longer pulling energy from warm tropical waters. The Joint Typhoon Warning Center on Hawaii has confirmed that the extratropical transition will be complete within roughly 12 hours of the morning of June 4th. The storm is now sitting in colder sea surface temperatures of 21 to 22 degrees Celsius with no residual ocean heat content available to refuel it. The direct wind and rain threat from this storm is over. But the ground across the Kanto region, Wakayama, Mie, and Shizuoka prefectures is still saturated. Swollen rivers, unstable hillsides, and waterlogged soil are still active hazards as of June 4th, even with the storm gone. Landslides can occur for days after a heavy rainfall event, as water continues to work its way through saturated soils. Pay attention to the slopes around your home and any hills above roads you travel on regularly through at least June 6th. Watch the Koza, Zenpakuji, Kanda, Meguro, and Nogawa rivers through June 6th. If any of those rivers are near your area, check the Japan Meteorological Agency's real-time river level tracker before assuming conditions are normal. The address is jma.go.jp. The emergency warning system is available in English. The 5-level alert framework is now active on that website with continuous updates. The waning 800 households in Ome in western Tokyo are still without running water as of June 4th. Restoration is expected to take several days. If you are in that area or know someone who is, do not assume water service has returned without checking with the Tokyo Metropolitan Government directly. The Municipal Water Department has been issuing updates through its official social media and emergency contact channels. National Route 371 in Kozagawa, Wakayama, is collapsed. If you are in the Kozagawa or Kushimoto area, do not assume that road is passable. Alternative routes through the mountain passes are available but may also have been affected by landslides. Check with the Prefectural Transportation Department before driving. High waves and rough seas are continuing along the Pacific coast from eastern Japan into southern Tohoku. The wave heights are not at storm levels but are still elevated above normal. Stay away from coastal areas and riverbanks through June 6th. For American military families at Yokosuka, Yokota, Kadena, and Futenma, both Japanese mainland installations have returned to normal operations. Schools reopened June 4th. The tropical cyclone condition of readiness has been lifted at all installations. On Okinawa, post-storm cleanup is ongoing, with downed trees and damaged power lines being addressed by base maintenance crews. Check the official Kadena Air Base and fleet activities. Yokosuka social media accounts for any updated advisories. The storm has passed, but the Japan Meteorological Agency continues to monitor residual landslide and flood risks in prefectures surrounding Tokyo. For the rest of the 2026 Pacific typhoon season, the Philippine Sea and the waters east of Taiwan are the formation zones to watch. That is where Jangmi came from. Sea surface temperatures in those regions remain well above the 26.5-degree formation threshold. The JTWC Pacific Storm Tracker at metalk.navy.mil updates continuously and is publicly available. If another named storm forms in the coming weeks, that is the first place it will appear in the operational forecasts. The Atlantic hurricane season also opened June 1st. NOAA's National Hurricane Center at nhc.noaa.gov tracks all active Atlantic systems and issues advisories whenever a tropical depression forms in the basin. The American Gulf Coast and Atlantic seaboard residents should bookmark that site for the rest of the season. The same global ocean conditions that produced Jangmi are part of the pattern that the Atlantic forecasters are watching for their basin. For anyone watching this from outside Japan or the United States, the relevant resources are the same. The World Meteorological Organization maintains a global tropical cyclone information page at wmo.int. Regional warning centers in your part of the world will use similar 5-level frameworks or equivalent systems. Familiarize yourself with what the levels mean in your country before a storm arrives. The time to learn the system is not when the alert is sounding on your phone at 5 a.m. The immediate threat from Jangmi is gone. The season it belongs to is not. On June 3, 2026, Typhoon Jangmi swept across Japan from Wakayama to the Kanto coast. It triggered the first Level 4 danger warning ever issued in Tokyo, and the first Level 5 emergency flood warning ever issued under Japan's new national alert system. At least 23 people were injured, 57 homes were damaged, and a highway in Wakayama collapsed. A morning in which 1-800 families in Ome, western Tokyo, turned on their taps and nothing came out. A morning in which the residents of Kozagawa looked at the road they would have driven to safety, and it was gone. A morning in which 1.6 million phones across the Tokyo metropolitan area sounded the loud emergency alert tone, and a reporter standing in an empty evacuation shelter in Shinagawa Ward counted the people who had come in. The count was one, and that one had gone home. This is not a story about one typhoon. This is a story about a warning system that fired correctly and a population that did not move, and a typhoon season with 5 months still to run. The data is what it is. The rivers rose, the warnings fired, and now the season continues. Pay attention to what comes next because the instruments already are.